There's a story that gets told a lot in the world of technology, and it goes something like this. Quantum computers are coming, and when they arrive, they're going to make every computer we have today look like a pocket calculator. Classical computers will be obsolete. Everything will change overnight. It is a dramatic story, and it gets a lot of clicks. But it is also, in nearly every important way, wrong. The real story of quantum versus classical computing is far more nuanced, far more interesting, and honestly, far more exciting than that oversimplified narrative. So today, let us do a genuine, honest, side-by-side comparison of these two types of computers, what they are good at, where they struggle, and what the future actually looks like when both of them exist in the world together. Let us start with classical computing because that is where most of us live. A classical computer processes information using bits. A bit is a unit of information that is always either a 0 or a 1. Every calculation your computer performs, every image it renders, every website it loads, every email it sends, all of it is built from enormous sequences of these binary digits being manipulated at incredible speed. Modern classical processors can execute billions of operations per second, and they do so with extraordinary reliability and precision. Your laptop does not randomly forget what it was doing. It does not need to be cooled to near absolute zero. It sits on your desk at room temperature, runs on a modest amount of electricity, and does exactly what you tell it to do, with an error rate that is vanishingly small. Classical computers are also endlessly programmable, meaning the same hardware can run a word processor, a video game, a web browser, and a machine learning model. They are general-purpose machines of staggering versatility, and decades of engineering progress have made them extraordinarily compact, affordable, and powerful. Now let us talk about what a quantum computer actually is. Without the hype, a quantum computer processes information using qubits. A qubit, unlike a classical bit, can exist in a superposition of 0 and 1 simultaneously, right up until it is measured. This is a real physical phenomenon, not a metaphor, rooted in the mathematics of quantum mechanics. On top of superposition, qubits can become entangled with one another, meaning the state of one qubit is correlated with the state of another in a way that has no classical equivalent. And quantum algorithms are designed to use a property called interference to steer calculations toward correct answers and away from wrong ones. These three properties, superposition, entanglement, and interference, are what give quantum computers their unique computational character. The word character is chosen deliberately here because quantum computers do not simply do everything classical computers do, only faster. They do something genuinely different. Here's where the comparison gets really important and where a lot of popular coverage goes wrong. Quantum computers are not universally faster than classical computers. They are not better at everything. In fact, for the vast majority of tasks that you and I use computers for every day, writing documents, browsing the web, streaming video, running spreadsheets, playing games, a quantum computer would be spectacularly bad. It would be slower, more error-prone, and absurdly more expensive to operate than the laptop already sitting on your desk. Quantum computers are not general-purpose machines, at least not in their current form and not based on our current understanding. They are specialized tools that offer a potential advantage for a specific and relatively narrow class of problems. So what kinds of problems might quantum computers eventually be better at? The most well-known example is factoring very large numbers. A classical computer, given a number with hundreds of digits, would take an astronomically long time to find its prime factors. This difficulty is actually the foundation of most modern encryption, including the RSA encryption that protects much of the internet today. In 1994, a mathematician named Peter Shor developed a quantum algorithm, now called Shor's algorithm, that could theoretically factor large numbers exponentially faster than any known classical algorithm. This is a genuine, mathematically proven quantum advantage for that specific problem. Another example is searching through large, unsorted datasets, where a quantum algorithm called Grover's algorithm offers a provable, though more modest, speed-up. Beyond these, quantum computers appear to be naturally well-suited to simulating quantum systems, modeling molecules, chemical reactions, and materials at the atomic level, because they are themselves quantum mechanical in nature. This has enormous potential implications for drug discovery, materials science, and chemistry. But here's the honest part that does not always make it into the headlines. We do not yet have a quantum computer that can actually do any of these things at a scale that matters in practice. The quantum computers that exist today are what scientists call noisy intermediate-scale quantum devices, NISQ machines. They have between a few dozen and a few hundred qubits, but those qubits are fragile, error-prone, and difficult to keep in a coherent quantum state for more than a tiny fraction of a second. Running Shor's algorithm to break real-world encryption would require millions of high-quality, error-corrected logical qubits. We currently have nowhere near that. The gap between what quantum computers can theoretically do and what they can actually do today is enormous, and filling that gap is one of the great engineering challenges of our time. Classical computers, meanwhile, are not standing still. The field of classical high-performance computing continues to advance, and in many cases, researchers working on quantum algorithms find that a clever classical algorithm can close the gap more than expected. There have been several high-profile cases where a problem that was thought to require quantum computing was later solved more efficiently than anticipated by an improved classical approach. This is not a reason to dismiss quantum computing. It is a reason to be intellectually honest about how the competition between these two paradigms is actually playing out. The most realistic picture of the future is not one where quantum computers replace classical computers. It is one where they work together. The phrase you will hear in research circles is hybrid classical quantum computing. In this model, a classical computer handles the parts of a problem it is good at: general logic, data management, user interfaces, error correction overhead, while a quantum processor is called upon to handle specific subroutines where quantum mechanics might offer an edge. This is already the approach being taken by IBM, Google, and most serious quantum computing research groups today. Quantum computing is real, the physics is real, the potential is real. But so are the challenges, the timelines, and the very important truth that classical computing is not going anywhere. These are two different tools, built from two different theories of physics, each with its own strengths and its own profound limitations. Understanding both of them honestly is the first step toward understanding what the quantum age will actually look like when it arrives.